Maybe he's waiting for me to log into the Zoom because I have.
He's there.
No, he just went. I think. So that he can.
So he said that we can. I don't know.
I'm not sure if this was Jose, but
Yes, the big guy.
He was saying we can.
Okay.
Okay, then I think we do. So welcome to this week's community seminar, and thanks for finding the time despite all the conferences that are ongoing here to come to this event, which is I think very competitive with these other conferences. And it's great to have Aitzol Garcia-Etxarri to present his work in this seminar series. Let me briefly introduce him. He studied telecommunication engineering at the University of Navarra and then physics at the UPOB, and obtained his PhD under the supervision of Pedro Giedke and Javier 2010. Went for a long postdoc stay to Stanford University and returned with a Gipuzkoa fellowship in 2015. Is a ICABASC research fellow since 2 years now, or
I don't even know.
okay.
2 or 3 years. 3 years.
And his the broad range of work, somehow I would say related always to nanophotonics in a sense, and on antenna on scattering from nanoscopic spheres. More recently, and that's where we had also opportunity to collaborate a bit on topological photonics, and also started a very interesting research line on the combination of nanophotonics and neuroscience. And there will be a conference that you may advertise in a couple of weeks, I think.
I forgot to do it.
And besides this, he's also a quite active science communicator. And those of you who know Basque, I think they can tune into the Basque radio station and hear him speak about science topics once a month. And today we'll talk about light-matter interaction at the nanoscale. And so please, Aitzol.
Thank you very much, Geza. So, yeah, that was a very nice introduction, quite broad and complete. And so, as you may know, I'm not the, our group is not the only group at the DIPC doing nanophotonics. There are some other groups like Alexei's group or Javier Pulva's group at the CFM, also joined with the DIPC. And so all of us work in nanophotonics, but of course, each of us has their own topics. And so trying to frame what we do in our group, I think that at the end of the day, I was trained as an engineer, and at the end of the day, like it or not, as much as I'm in love with the idea of discovering new knowledge, going through the contributions that we have made in the last years, I think what we are doing the best that we can is finding applications to these nanoscale light matter interactions, to the developments in the field of nanophotonics. So today I will present the main research lines in our group. And you will see that if I would present them one by one in different talks, they might seem completely different topics, but I'll try to do my best to explain you that at the heart of all of them, the same stuff lies, which is basically the interaction of light with nanostructured matter, which is what we do in our group. So basically solving Maxwell's equations in complex environments. All right, so I'll go topic by topic and I skip the first introduction, let's say, to nanoscale light matter interactions, because otherwise the talk was too long, but I don't think you will have any problems following what I will present. So the first line of research that I would like to talk about is our oldest line of research, and deals with chiral light matter interactions. So the interaction between chiral matter, chiral molecules, with chiral light, meaning circularly polarized fields. So why is chiral matter important? Or maybe what is chiral matter? I guess you're all familiar with these ideas, but no matter what, chiral molecules, let's say, are those molecules that even if they have the same molecular formula, here I'm showing one example of an infamous example of thalidomide. So this is one, what I never know how to pronounce, stoichiometric, well, the formula of the molecule. But when the molecule comes into real life, let's say, it can take two different spatial configurations. One is here, and the other one is the mirror image of the one here. These two possibilities, well, the molecules are super similar to each other. They have the same physical properties, but the spatial configuration is different. Why? Because they are chiral enantiomers of each other. If you want to understand chiral enantiomers in a very simple way, we have the example of our two hands, the left hand and the right hand. Both are mirror images of each other. They look identical, but now if you try to superimpose one hand on top of the other, taking into account that the front and the back are different, you will notice that you cannot superimpose your left hand on top of the right hand using rotations by themselves, right? So those are chiral objects, chiral molecules in particular. And why are chiral molecules important? So basically, because most of our biologically relevant molecules in the body are chiral molecules. So I'm talking about proteins, amino acids, sugars, all of those are usually chiral molecules. And very importantly, chiral objects interact differently with some chiral objects depending on their handedness, okay, if they are right-handed or left-handed. Also for kids, but if you want to test this, you can try giving your left hand to the left hand of somebody sitting by you, and you will see that you will produce a handshake, a regular handshake. But if you offer your left hand and the other person gives you the right hand, you will see that hands don't match, okay? So that's the interaction between chiral objects, and it happens at every single scale in the universe. And so if a chiral molecule, let's say a protein in your body, wants to, well, interacts with another molecule, let's say a drug, some medicine that your doctor prescribes you, and if this medicine is chiral, depending on the handedness of the protein itself and the drug, the interaction can be different, and the effects that this interaction will produce in your body will be different. I mentioned previously that the case of thalidomide is particularly infamous. So thalidomide is a molecule that was discovered or started being used as a drug in the 50s of the previous century. And they discovered very quickly that it was very useful to treat morning nausea on pregnant women. But unfortunately, sometime after, they noticed that a lot of women that were treated with thalidomide were giving birth to children that were born with defects in their bodies. They didn't know what was going on in the very beginning, and it was a Spanish researcher with a German name, Klaus Kneip, I think it was his name, but nevertheless, he was born in Madrid and he was from Madrid, discovered that what was going on is that actually thalidomide was a chiral molecule, and that as a chiral molecule, it had two enantiomer versions. And so one of the enantiomers was doing what the drug was supposed to do, was treating morning nausea on pregnant women correctly, but the other enantiomer, the R enantiomer, was inducing birth defects in the fetus. Okay, and so since then, I gotta say that 50% of the molecules that we use as drugs nowadays in the pharmaceutical industry are chiral molecules. And since 1992, if you want to commercialize a drug which is chiral, the FDA forces you to sell it on its enantiopure form, meaning that you can only, that the drug can only contain the good molecule and cannot contain any of the other molecules. Nevertheless, going back to the topic, I said that I had 22 slides, so it would take me like 2 hours and a half to go through this. No, it always happens to me, this first slide. I never know how much people know, and so I always end up explaining everything. So, but after what I explained, you can see that it is very important to study molecular chirality, to know what the chirality of molecules is, and how can we do it. So we can use light to study the chirality of chiral matter. Why? Because light, as you probably know, has a very special property, which is the polarization of light. Okay, you know that light are, well, you can understand them. Geza is here, so forgive me, Geza, but light can be understood as a classical wave. Let's put it that way. And this wave is a vectorial wave, which can oscillate up and down, left or right, or with linear combinations of these two possibilities, giving rise to left-handed circularly polarized light and right-handed circularly polarized light. These two solutions to Maxwell's equations in free space are chiral enantiomers of each other. And as I already explained, chiral objects, chiral entities interact differently depending on their handedness. And so if we have one particular chiral molecule, I'm showing here a DNA strand, but basically because it's something like a helix, which is the archetypical example of chirality. We have one particular molecule. So this molecule and this molecule are the same molecule with the same handedness. Now, if we illuminate the molecule with right-handed circularly polarized light, the molecule will absorb a percentage of the energy that it's feeling, okay? Following a rate of absorption, A+, we will call it here. Now, if we illuminate the same molecule with left-handed circularly polarized light, the molecule will also absorb light, but the amount of energy that it will absorb will be different. Why? Because this chiral light, this chiral interaction will be different depending on the handedness of the light and the molecule. Okay, so what we can do is measure in a lab, we can measure how much light has been absorbed when I was exciting my molecule or my sample with right-handed circularly polarized light, measure how much light was absorbed with left-handed circularly polarized light. And now, since these two quantities are different, I can take the difference, and we call this difference the circular dichroism spectra of the matter, the molecules that we are studying. And this circular dichroism spectra will give us information about the chirality present in our molecules, in the matter that we are studying. Okay, the problem here is that these absorption rates are super small compared to the regular, let's say, absorption rates of the molecules, not to circularly polarized light, but to linearly polarized light or something like that. So basically, these circular dichroism signals are always super, super small. And in order to measure something significant, you need either to have a lot of chiral matter and illuminate it with light, or to integrate through long periods of time the interaction of light with these chiral molecules. So circular dichroism spectroscopy is widely used nowadays in many areas of research and pharmacology. But what we want to do in this first line of research is use the field enhancement properties that nanoparticles can present to augment the sensitivity of circular dichroism spectroscopy. Since you are working at the DIPC CFM in our environment, you will probably know that nanoparticles, plasmonic nanoparticles in particular, have been used throughout, 20 years or something like that, to augment the sensitivity of many spectroscopic techniques, such as Raman spectroscopy or infrared absorption spectroscopy. Why? Because these nanoparticles can act as, we call them in the outreach efforts that we do, as gold nanolenses, okay, the plasmonic ones. Why? Because they are able to concentrate light at the nanoscale very, very efficiently. The same way when we were kids, we used lenses to concentrate light on pieces of paper and burn them. You remember that? But nanoparticles can do the same thing, but with much higher efficiency and much better localization in real space. Okay, so since year 2013, more or less, when I was a postdoc at Stanford, we've been trying to take those ideas and bring them to the universe of chiral light matter interactions and determine first, that was our first contribution in 2013, first determine what were the necessary and sufficient conditions to achieve this sort of enhanced chiral light matter interactions using nanoparticles. And we concluded that you needed both electric dipoles and magnetic dipoles in the nanoparticles that you wanted to use. In order to enhance Raman spectroscopy, infrared absorption, etc., you're fine just enhancing the electric fields of light. But in order to augment chiral light matter interactions, we determined that you also needed to augment to control magnetic fields in the surrounding of the nanoparticles. Okay, so that's all news, almost 10 years old. And so in our group nowadays, Jon Lasa Alonso, well, this is from 2020, so it's a couple of years old, but nevertheless, he's still working in these topics. What we showed in this year is that you can actually use not single nanoparticles, but arrays of nanoparticles to produce what is called lattice resonances, which are resonances that you can get in the spectral regime, which very sharp features and very intense features, okay? And we proved here that these lattice resonances on high-index nanoparticles present in electric dipoles and magnetic dipoles could be super useful to augment circular dichroism spectroscopy up to factors of 1 order to, 2 orders, 3 orders of magnitude or something like that. Okay, so we are still working in these topics, also with Jesus Ugalde, who is a university professor also working here at the DIPC, and Vladimir Mujica, and many people from that line doing ab initio studies on molecules and so on. All right, not only that, so one thing is to study chiral properties of matter, but as I told you, producing chiral drugs is something quite difficult even nowadays, because if you try to synthesize a chiral drug without doing any tricks whatsoever, you will always get 50% of one version of the molecule and 50% of the other. So you need to introduce modifications to the synthesis processes. The one most probably used, I'm talking in front of chemists here, and so I'm getting a little bit nervous because I'm not a chemist and I don't know too much about these things, but I know they use chiral amplification, chiral catalysis, okay, which was a discovery that was done in the 60s, more or less, or 70s, and they got a Nobel Prize in the 90s for this development. And so by introducing some catalysts in the reaction, which are chiral, you can actually produce not 50-50, but maybe, I don't know, 70-80%, and then use separation techniques to get an enantiopure, just one version of the molecule and not the other. All right, these chiral catalysis procedures are super useful, but they have a big problem, which is that you need to find the reaction for every family of molecules that you want to synthesize. And so if you check Nature or Science in a weekly basis, the titulares in Spanish, the headlines at least, you can see that every 1 or 2 weeks there is some new chiral catalysis, blah, 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 in some Nature Science paper. Why? Because still nowadays it's a super relevant problem to keep finding methods to separate chiral molecules of different kinds. Okay, but another thing that you can do is use these selective chiral light matter interactions to produce photolysis events in certain molecules and not in the others. Explaining it, I'm going to try to be fast, but I don't know if I will succeed. So now in this case, imagine that you have a solution with 50% of one enantiomer of a molecule and 50% of the other. And now you illuminate this solution with circularly polarized light of one particular kind. Let's say right-handed circularly polarized light. These molecules, as before, will absorb some, I don't know, percentage of the light that is getting to them. But since the molecules are chiral and then present different chiralities, right-handed molecules will absorb an amount of energy, and left-handed molecules will absorb a different amount of energy. All right. Now you can imagine that you could start increasing the power of your laser, illuminating this solution of nanoparticles, up to a threshold where a molecule is absorbing more light than the other. And the threshold that I'm talking about is the threshold where the molecule absorbing a lot of light is absorbing so much light that can induce, that can generate a photolysis event, let's say a break in some bonds in the molecule or something like that. So the threshold would be the threshold where one enantiomer of the molecule gets burned, talking like very hand wavily, but the other one is not. You see more or less the idea. So you illuminate the solution with circularly polarized light, you increase the power, and if you play well with the power and the thresholds, you can get some molecules to be destroyed or transformed into something else, while the other molecules are remaining intact. This is something that works, and it's been known also for decades, but it's a super inefficient process, because basically what you achieve is that you burn 99% of the molecules, 100th or the other, and then from the remaining 1%, you can observe that actually, yes, you burn more of one kind than the other, but actually you cannot use this method for industrial purposes because you're losing everything that you started from. And so another thing that we've been trying to do for for quite a long time, also since I was a postdoc at Stanford, is to use nanoparticles to augment the efficiency of this separation process, of these photolysis events. You can also do it with photoionization, but it's slightly more difficult to understand, so I stick to photolysis. And so in this work in 2019, we proved for the first time that you can use arrays of nanoparticles, also presenting electric dipoles and magnetic dipoles. It turns out that magnetic dipoles are more important for this application, but if you're interested, read the paper, please. And so in this graph, well, it's a bit complicated, but what we proved in this graph is that if you use bare light with no nanoparticles, as I said before, the remaining molecules that you will get are very few and the process is very inefficient. But if you use these arrays of nanoparticles to control, to engineer light matter interactions at the nanoscale, that you can get enantiomeric excesses, which means like how much of one kind versus the other one you get in the solution, which are very considerable with quite considerable yield. Let's say like how many molecules are remaining in your solution after the process that you put the molecules under. Okay, so one more approach to separate chiral molecules is to use optical forces, meaning that when you know that light can exert forces, can transfer momentum into matter, and if the matter is chiral and light is chiral, this momentum transfer is also different when you use right-handed circularly polarized light or left-handed circularly polarized light, or if you stick to right-handed circularly polarized light, but you have right-handed molecules and left-handed molecules, right-handed molecules will perceive some forces and the other molecules will perceive some other forces. So these are called enantioselective optical forces, and Jorge Olmos Trigo, who's a postdoc in our group right now, is studying this sort of light matter interactions. Okay, this is the first part of the talk. And now we will change gears for the first time, but we will change gears 3 or 4 times during this talk, quite dramatically, to a different topic, topological photonics. So this half of the audience, except one person, is quite familiar with this topic, and the other half, I don't think is so familiar with this topic. So this half, forgive me if I say something stupid, and this half, forgive me if you don't understand anything of what I say, because I don't have too much time to go through this topic either. Okay, so this is a completely different application of nanoscale light matter interactions. And actually, in this line of research, we will not focus in the interaction between light and nanoparticles, and we will focus in the interaction of light with photonic crystals. Photonic crystals are periodic arrangements of objects in space. It can be in 2-dimensional space, it can be in 3-dimensional space. And thanks to this periodicity, you can get the propagation of light through these periodic objects to behave more or less similar to the behavior of electrons in solid state. Okay, because we also have wave functions and they are periodic, this and that. You can apply the Bloch theorem that you probably are more familiar with in the solid state universe. And so you can get very similar effects. You can get band gaps, for example, like ranges of frequencies where light cannot propagate through. In the case of electrons, you know that the ranges of frequencies where electrons cannot live, let's say, etc., etc. In particular, in 2008, 2009, more or less, the group of Soliacic at MIT discovered that you can not only produce band gaps in photonic crystals, but they proved that these band gaps could also present some very special properties that solid state systems presented. In particular, they focused in the quantum Hall effect, in this case of light, because they were using photonic crystals and light. So what they basically proved is that if you have a photonic crystal here, a square array of rods, if you calculate the band structure of this photonic crystal, you have it here, and you can see that there is a band gap here between certain energies, and in particular, you have a twofold degeneracy at the endpoint. All right, and so they proved that now, if you magnetize this system, if you apply a magnetic field to this system, this twofold degeneracy is lifted, and you can get a second band gap here. And now, if you calculate the Chiral number, which is the, let's say, the topological invariant quantifying the capabilities of your system to present the quantum Hall effect, okay, in solid state systems, I mean, They proved, I mean, you can calculate these quantities in photonic crystals as well, because you have eigenvalues, you have eigenvectors, everything is periodic, you have the block theorem, everything is more or less sustained. And so they proved that this band structure had a non-trivial topological character. In particular, they created a surface. I don't know where it was, the surface. Well, I think it's in this direction, not in the other one. And they showed that you can get an edge state, which is something that you get in the quantum Hall effect in solid-state physics as well. Not only that, they also proved that this edge state was topologically protected against backscattering, which is exactly the same thing that happens in the quantum Hall effect for electrons. And so this is the photonic crystal, the square lattice that I was telling you before, the one that presents topological properties. And this is a trivial insulator, some other material that will allow light to, let's say, that will not allow light to escape from the system, because unlike in electronic systems, in photonic systems, light can propagate through free space inside the light cone, and well, technical details, but you need an insulator, a real insulator, to block light from escaping from there. And they proved that this edge state that they were getting here was super efficient in propagating light through the edge and only through the edge. You can see that there is nothing in the bulk and nothing in the bulk here. So light is only in the edge. And now they started playing with some defects that they were putting in the way, some obstacles. And they proved that this topological protection against backscattering was also solid and in photonic systems. Okay, this is work by some other people who are brilliant, idols to me. And so, but when we saw this, no, it's not when we saw this. So I came back from Stanford in 2015, more or less. And by those years, I was the roommate of Maya García-Etxarri, who has been an incredibly good friend of mine since we started doing the PhD together. And she was already working in topological materials. And so we would talk about our lives and our works when we were at home and when we were at work. And they started developing this tool that you probably heard about, topological quantum chemistry, that allows you to determine the topological properties of solid-state materials just using group theory without needing to go through calculations of very complex topological invariants, etc. Right? And so around year 2016, 17, something like that, Maria Blanco de Paz joined our group. Maria Blanco de Paz was co-supervised by me and Darío Berciu, who also works in topological materials. And we decided to apply this method that Maya and her collaborators were developing to photonic crystals for the first time. And that's what we did. We applied topological quantum chemistry to photonic crystals. And by doing so, we discovered a couple interesting things in those years. So first of all, we discovered a topological phase that was predicted some years ago, but is still inexistent in any realizable material. And we found the first instance of this so-called fragile topological phase that I will not explain in much details in photonic crystals. And also we proved that some topological systems that, well, some photonic systems that were thought to be topological, that they were not so topological as some people expected. We did that with the thanks to topological quantum chemistry, because it's incredibly fast, incredibly good, and incredibly insightful to determine the topological properties of several materials. Okay, then since I told you, I mean, Maria was co-supervised with Darío Berciu, and Darío Berciu was supervising Miguel Ángel Herrera, who is not working in photonics. He is working in electronic systems, and in particular in quantum simulators. So surfaces of certain materials where you can place molecules and create periodic potentials more or less at will. And so that's how I got introduced to this sort of quantum simulators. And we are also developing quite a lot of research in this area. Well, Miguel Ángel is the one developing the research, and we are supervising it the best that we can. Okay, but then everything that I talked about topological materials up to now has been in 2 dimensions. So in photonics, that means objects that are invariant along the z direction. So infinite cylinders, infinite objects in one particular direction. But Chiara de Vescovi, who is another PhD student at the DIPC, started working with Maya García-Etxarri and me. She's co-supervised by both of us around year 2019 or 18, more or less. And so we decided to go from 2 dimensions to 3 dimensions, which is a much more complicated, let's say, system to understand. But nevertheless, the first challenge that we imposed ourselves was to find the quantum Hall effect that I explained you before for light. We call them in this work 2D Chern insulators. It's another alternative name to the same effect. But the challenge that we posted to Chiara was to take the 2D quantum Hall effect and find a 3D equivalent in photonic systems. You can do that because photons are bosons and they are not fermions. In solid-state systems, it is very well known that you cannot get 3D Chern effects. You can get them as layers of 2D Chern insulators, but nevertheless, what we wanted to find was a system. You can see that here we have cylinders, here we have spheres. This is a schematic where you could get these topologically protected edge states. But now, if we would change the orientation of the magnetic field, the magnetization axis, we wanted to get edge states that would go always perpendicular to the magnetic field, no matter which direction you would put the magnetic field on. In 2 dimensions, you can only do it in one direction in particular. Okay, so nowadays we are also working with Antonio Morales, who is not here. I didn't have a photo of him, but he is doing the master thesis and started at the DIPC 1 month ago. And Antonio and Chiara are doing amazing work together these days. But nevertheless, going back to the 3D Chern insulators, basically I want to say that it was a long route, but we managed to do it. And it works very, very well. And so this work was published last year in Nature Communications in December. It's not in press, it's been published for months, but this slide is old. My apologies for not updating it. And so, okay, with this, I will close the second chapter of this talk. And we go for the third line of research that we started developing also in 2019, more or less. A little bit of history. I don't know if you know who Rafael Yuste is, but he's a neuroscientist, a very well-known neuroscientist worldwide, who is a professor at Columbia University. Okay, so Rafa started visiting the DIPC around, I don't know, 2018 or something like that. And it turns out that Rafa was a very good friend of one of my best friends from my years in San Francisco. So my friend these days is not a neuroscientist, but back in the day he was a neuroscientist. And so I saw one of Rafa's talks in Passion for Knowledge in particular, this amazing festival that the DIPC organizes every 2-3 years. And I wrote my friend Mario and asked him, Mario, by any chance, do you know this guy Rafael Yuste? It's the first time I hear about him and I'm wondered by what he's doing. And he told me like, oh yes, he was a very good friend of mine, say hi. Through this friend in common, I started talking to Rafa, and turns out that Rafa wanted to do some research in San Sebastian. And basically, as you can perceive from this talk that I'm giving, I get excited about anything which is new and exciting. And so when he told me that he wanted to do research on neuroscience in San Sebastian, we tried to find a, I don't know, common topic to work together on this. He wanted a partner in crime, and I wanted to work with him. And so we started developing ideas to apply the capabilities of nanoscience, in particular of nanophotonics, to the neurosciences. And that's how the Nano project was conceived. Since then, it grew a lot. I will explain you about the growth and the current status of the team that is working in Neuro in a minute. But in a couple of words, I'll try to explain you the general ideas, and I'll try to convince you that I'm not crazy, that what we want to do is actually what we've been doing for more than 15 years, but basically applied on something new, as I was telling you before. So if you have a nanoparticle, I was going to go all the way to the outreach thing, and a particle which is very, very small, like 10,000 times more than, no. If you take a gold nanoparticle, a metallic nanoparticle, for example, and if the nanoparticle is small, if you excite it with light, these metallic nanoparticles present some very special properties in their light-matter interactions, because you can excite surface plasmon resonances in the nanoparticles if they are made of gold. All right. So if you analyze, for example, the absorption of this nanoparticle to light of different wavelengths, you can construct this sort of spectra. And in this spectra, you can see that the absorption of light by the gold nanoparticle presents a resonance around 500 and something nanometers. This wavelength depends on the particular designs of the nanoparticles, but whatever. And so the nanoparticles are made of metal. And what happens when you move electrons to one side and the other inside a metal? That the metal heats up, basically. That's known as the Joule effect. And I'm assuming that you all know what I'm talking about, right? So metals heat up when electrons are excited inside them. And so one thing that you can do many things with these nanoparticles. You can augment surface enhanced spectroscopies. You can do super high resolution microscopies using these nanoparticles. For example, Rainer Hillenbrand and Alexei Nikitin work in that line of research. But another thing that you can do with these nanoparticles is use this heat in very special ways. Why? Because if you think about it, this nanoparticle in particular is 10 nanometers in diameter. If you illuminate it with light, the nanoparticle will heat up, as I just explained you, but what you will get at the end of the day is a source of heat, which is 10 nanometers in diameter, and nothing more than that. So these nanoparticles can act as super localized sources of heat. These sources, well, this spectra that you see here is the temperature increase that you can get inside the nanoparticle for different frequencies, excitation frequencies of light. And you can see that around 520 something nanometers at the plasmonic resonance, you can get an increment of 2 to 3 degrees in the temperature of the nanoparticle. Well, this is a cross-section of the near field of the nanoparticle, so what happens close to the nanoparticle. And you can see that inside the nanoparticle, you can get an enhancement of, well, not enhancement, a temperature increase of 6 degrees, more or less. And outside, you can get temperature increases of 3 or 2 or something like that, until, of course, if you go far away, you don't see any temperature increase whatsoever. Okay, so you might think that a temperature increase of 6 degrees is not very relevant because it's not a temperature increase of 60 or 600 or 6,000, but in our bodies, the cells in our body, if they get heated by a couple degrees or 6 degrees or just a tiny little bit of temperature increase can have huge consequences in our body. Well, you know that when we get a fever, we don't get fevers of 62 degrees. We get fevers that are basically 3-4 degrees above our regular temperature. And I mean, that's an indication of the effect of a temperature increase in our body. It's a big effect. And so with these temperature increases, back in the day in 2000, I don't want to say anything stupid, 2006, 7, 8, something like that, when I was doing my PhD, Naomi Halas, who is another good friend of the DIPC from Rice University in Texas, in the US, developed a method to treat tumors in living patients. Why? Because she was able to take these nanoparticles, functionalize them with a very concrete layer of molecules so that the nanoparticles would attach to cancerous cells, but not to healthy cells, all right? So that's what she did. Then she would illuminate them with infrared light because our bodies are slightly transparent to infrared light. And through these temperature increases, they were able to burn the tumors, but without affecting any healthy cell at all. Then the burned tumors would be expelled from our bodies in the form of, well, you can imagine the form, but basically the same way that we eat, our body expels the rest, right? And so that's an application that has been under development for more than 10 years. And as far as I know, it has been successfully applied in prostate cancer and it's working well. And so inspired by all of those previous results in some other biologically relevant but different topics, in the group of Rafael Giedke, in 2018, they proved that you could use these nanoparticles not to destroy, but to excite neurons in living organisms, okay? Both in vitro, so let's say in cultured neurons, but also in particular in this paper, they did it in Hydra, which is a very, very small animal with very few neurons. And so what they did was basically the same thing. You can see the nanoparticle here, these yellow dots. They covered the nanoparticles with some molecules that would attach to the neurons. they, with a syringe, this was, I mean, the first try that they did, with a syringe, they placed the nanoparticles around the sample that they wanted to study, the nanoparticles attached to the neurons, and then using some very special lasers that they have, they excited the system made of neurons and nanoparticles, and they could observe that the neurons would fire when you would excite them with light and stop firing when you would not illuminate the sample. So this was the, let's say, the proof of concept that we needed, and it was done in Rafa's lab. And with this initial impulse, we decided to start working in this area of research. Why? Because basically, I mean, I spent more than a decade designing nanoparticles, say during my PhD, etc. And nowadays, I'm not going to say it's easy, it's difficult, but we know very well how to do it here at the DIPC at CFM. So it's one of our strengths. And Rafa, in those initial stages, was going to take charge of all the biology, which we have no idea about. All right, that's how we started, but soon more people joined the project, the crazy project between the Marek, who is sitting here, and I will explain you now how. But most importantly, I want to mention Teresa Zelaya, who's also in the audience here, Javier Alfaro, who is in New York right now in Rafael Justes' lab, trying to reproduce these experiments so that we can do them later here, and Maria, who is working in Nachucarro, that you know that they do a lot of neuroscience in vivo. And so these people are the first people that we hired at the DIPC to work in this project. And so Teresa is doing her PhD, and Javier and Maria are postdocs. All right. So I showed you how to excite neurons, but we also want to read signals from neurons using nanoparticles. And in order to do that, we don't really know exactly how we're going to do it yet, because there are several strategies on top of the table right now. But one thing that you could do is use quantum dots instead of plasmonic nanoparticles. Why? Because quantum dots have a photoluminescence, which depends on the electric fields that they perceive. This is known as the Stark effect. And so these are two very particular strategies that people followed in the past to read signals from neurons using quantum dots. Maybe the easiest one to understand is this one. So this is the neuronal membrane, the membrane outside the neuron. So what they did is place quantum dots inside the membrane. And when a neuron fires, it creates very strong electric fields across the membrane. Like if it could be a capacitor, imagine that this is a capacitor, one plate and the other plate. So the neurons or the cells in your body have also these two layers. And if you place a quantum dot inside here, you can check the luminescence of this quantum dot, and depending on if the neuron is firing or not, the luminescence will be different. Okay, so using this, they proved that they could track the firing of the neuron with quite a good accuracy. Also using charge transfer mechanisms, they could do it. There are many strategies, as I told you, on top of the table. So, but these are some ideas that we have. Well, now I come to a little bit of the history of how the project developed. So, well, first of all, Raf and me, we started organizing a conference, the Neuro conference in 2020. That was the first edition. As Geza mentioned, the third edition of the conference is going to take place the 21st of July this year. The conference is online and it's absolutely free. If you are interested, I didn't include the advertising here, but follow me on Twitter and you will find it there. That's the easiest thing. Otherwise, send me an email, but I think it's easier to get all the spam that I send through Twitter. García-Etxarri. It's not. Well, nevertheless, after the first conference that we organized, we wrote an article. The title was Time for Neuro. That's why I used the same title for this section of the talk. And after that, we started designing a plan on how to do these experiments much better than they did in the past. We realized that the key was to design everything from very first principles. Basically, in the experiments that Giedke did in his lab in 2018, they took some gold nanoparticles that they had there, basically, so super small nanoparticles that you can buy online, but they were not designed for this purpose whatsoever. And so that's where we started from. But then we realized we need to synthesize these nanoparticles properly. Luckily for us, we had Marek next door, who knows a lot about synthesis of nanoparticles. And so Marek joined us in the team, and nowadays is a fundamental part of this whole crazy business. And so at the CFM, Soon, Susana joined as a PhD student, then Anne as a postdoc, etc., and the team kept growing. And nowadays, I wanted to mention that we have plans to do these experiments. We are actually doing these experiments, but step by step, in the Basque country. And we call our plans these days the Basque Nano Network. And why? Because we work as a network at this point as a virtual lab between 7 different centers, 6 in the Basque country, and then Columbia University in New York, in the States. And so some words, so at the DIPC, we are very good at the design of nanoparticles, and that's what we will do. At the MPC or CFM, in Marek's team, they are incredibly good at the synthesis side of the problem, so they will do the synthesis. In biophysica, there is one woman who is amazing, Monica Carril, in functionalization of nanoparticles, in particular, orthogonal functionalization of nanoparticles, so that the nanoparticles that we will use will go exactly what we want them to go. It can be a particular channel in a neuron, or any channel, but in one particular kind of neuron and not a different kind of neuron, etc., etc., etc. So Monica Carril in biophysica will be in charge of the functionalization of the nanoparticles. We have Biodonostia also in the team. Why? Because they are super good doing in vitro experiments, and actually Anne is doing most of, well, part of her work there in Biodonostia these days, culturing cells, growing them in the particular environments that we need them, doing microscopy on them, etc., etc. But then we want to do experiments in vivo, and Achucarro, well, Abraham Martin from Achucarro also decided to join our team. And Maria, who's a postdoc hired by the DIPC, is working at Achucarro right now. And we are already doing our first surgeries in mice and rats, which is quite impressive. And I don't recommend you to see it. I saw it last week and I'm still traumatized. But nevertheless, a final piece in the Basque country is Tecnalia, because they are amazingly good at technology transfer. And not only that, they were the ones that decided to ask for money to Europe, and they basically coordinated all of us, the 7 centers that you see here, in an amazing manner. And nowadays, Ander Ramos and Iñaki Ortego in Tecnalia are very important people also in this project. And last but not least, we have the Neuro Technology Center. This is basically Rafael Justes Lab in New York City, where we are, first of all, going to learn how to do these experiments. And Javier Alfaro, who is there right now, is doing an amazing job at that. He's the one that showed us I'm going to be clear, the insights of a mice last week. And so I'm fascinated by how somebody who, was an expert in nanophotonics and in a nanophotonics lab or something like that was doing surgeries in a couple of weeks. Quite mind-blowing. And not only that, they are worldwide experts in holographic experiments, illuminating with light certain areas of the brain, certain neurons, particular neurons in the brain, etc., etc., etc. And of course, Rafa started all of this with us here in San Sebastian, and he is the central piece, let's say, that joined us all around this Nano project. Okay, you might think that the talk is over, but no, there is one more topic, which is something that we started not too long ago, machine learning for nanophotonics, with Proyecto Final de Grado of Edurne Science, who is here. And so in this last line of research, what we want to do is use the power of machine learning to be able to simulate the optical response of nanostructures. Why? Because these simulations of the optical response of anything, a plasmonic nanoparticle, a dielectric array, whatsoever, it might not seem very complicated, but calculations get crazy complicated super, super fast. And so I've been running, well, in the past, I ran simulations in Atlas, you know Atlas very, very well, for, I don't know, weeks, even months, to calculate the optical response of a nanorod, for example, a work that I did with Javier Ezpurua. And Teresa nowadays is doing a lot of calculations there, and she knows very, very well that some calculations can take pretty much forever. But machine learning can help us here, because I'm not going to explain what machine learning is whatsoever, but you can use neural networks, train them using data that you calculated in the past, so that the network can generate the optical response, in our case, of some nanoparticle, a guess of the optical network of the optical response of a nanoparticle, that then you can use, for example, to use it as input for your calculation so that the machine calculates everything way faster. And so we can do super fast calculations using machine learning. These are just some results that Edurne developed with Nuno da Souza, who is another DIPC member last year. And so you can say, you can see here, this is the exact solution to one particular configuration, one particular nanoparticle. And this is the output that you get using convolutional neural networks. And so you get a precision of 85%, but the DDA method, the exact solution to Maxwell's equations, can take 8 minutes. This is not very complicated. I mean, 8 minutes is not too much, but you can easily scale up. But the most important message here is that using the neural network, you can do the same calculation using 10 to the minus 2 seconds. So you can see how you can gain orders of magnitude by using machine learning. Nevertheless, I think this is it. Yes. So we have seen that nanophotonics can be used in many different areas. And if something, since this is an internal seminar and whatever, the take-out message that I would like you to take is that in our group, we basically take the possibilities that nanophotonics is offering us to apply it to different problems that might have a relevance or an interest to us in particular. This is it. And if you have questions, now go ahead.
So for the great and broad talk, so there's time for questions. Here, presential one, also in the online audience, we had about 10 spectators from the outside. And but I think you're first to start.
I thought there was a particular.
Thank you very much for nice talk. I have a question to the last part. Can you comment on the architecture of the network you use? I mean, this is a deep learning.
Oh, I think I ran out of. That is a mess, but yes, it is deep learning, but it's a convolutional neural network. In particular, the name of the network that we use is UNet. And UNet, it's because, well, that name is because it has a little bit the shape of a U. It starts from very long chains of neurons. We have to be careful here because we've been talking about real neurons and not so real neurons. And then that layer gets smaller, 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 and then until it becomes a layer of how many neurons, Edurne, in the intermediate layer? Very few. Yeah, very few neurons, and then you grow it out again until you get the solution, let's say, or the layer that gives you the solution. And so we used this network because it's especially good for predicting images. Okay. And so at the end of the day, what we are doing, electromagnetic fields are vectorial, but imagine that they are scalar for a minute. And so the solution to Maxwell's equations, you can understand it as an image. Okay. And you want to predict, well, yeah, and the inputs that you give to the neural network is also a drawing, let's say a drawing of a nanoparticle, right? And so we're giving the neural network an image and we want to predict the output, which will be another image. And so following that intuition and also following a paper that was published 2 years before, because what we did in this first work is reproduce another paper, we decided to take that route and use these convolutional neural networks, in particular the UNet architecture.
So in this last slide, you represented colors, and then I didn't get basically what you show in these two axes, actually.
Vale. I'm sorry, because I ran out of battery right when I finished the talk, and I screwed up the whole thing. But the axes are basically, so what we were showing there is near field plots. So fields around the nanoparticle. X was the x-axis, Y was the y-axis, and the color was the intensity of one component of the electromagnetic field. I think we were plotting the real part of that component. The first line was one component, E sub x, oh, great. And the other component was E sub y. Okay, is there any other question?
questions? I have one.
Real part and imaginary part of physics. Details at the end of the day.
And kind of related to the first and second part of the talk. So,
okay.
Would it make sense, or can one design photonic crystals that have chiral bands so that you can enhance these enantiomeric separation because you sort of provide a whole band instead of?
It's a very good question. It's strongly related to something that we are exploring also in some other realms that I didn't include here, which is called the SIS effect, the chiral induced spin selectivity. Mm-hmm. And it is a very good question. It doesn't have a very simple answer. So intuitively, the answer is yes. But then when you start working hands-on the problem, which we tried with Chiara in her paper, because her system is non-chiral, and so we said that, okay, then these H states, they have to have some spin momentum locking and this and that. You quickly realize that working with bosons, when you want to talk about spin, is way more complicated than working with fermions, and working with fermions is already quite complicated. Actually, I think we talked in the past, well, I don't know, but yeah, to discern what we could extract, what information we could extract about the spin of light using classical electromagnetic simulations. And so it's something that we want to explore, and hopefully we will explore soon enough. We're looking for funding to start another PhD thesis on those topics.
Okay, thanks.
Sí.
So online there are no questions. So
I have questions regarding the chiral photonic structures. Do you have any insight on how circularly polarized light would be transported along these? Let's say I have a chiral photonic structure, and then instead, because the light you inject, is it linearly polarized, or is it?
It can be whatever you want.
Whatever.
Yeah.
But would there be a difference? I mean, okay, I have an idea, but
yeah. So the quick answer is yes. They have to be different. If your object is chiral, due to these chiral light matter interactions that I explained, or how you give your right hand to the right hand of the other person, etc. If the object is chiral, you know from the beginning that the interaction will be different for a left-handed excitation or right-handed excitation. It's a good starting point. But then, determining ideally, you know that in the quantum Hall, in a quantum Hall system, and I'm saying that you know because I know you know, you know that the H state is chiral. Okay, so the spin is very well defined, and you have the spin momentum locking and all of that. In photonics, in order to check if that is true, we would need, strongly related to what Geza was asking, we would need a method to determine the spin of the electromagnetic fields excited in that surface state. Imagine for a minute that the spin is well defined and that you have exactly the same thing that you have in a quantum Hall system in solid state. What that would mean is that if I would excite this H state with the right polarization, then I would have a mathematical overlap between the input that I'm putting into my system and the eigenstates that I will excite. That would mean that I would be able to excite these states. On the other hand, if I would use the opposite chirality for the excitation, if the chirality or if the spin of the H state is well defined, if I would use the opposite chirality to the one that I want, those two states would be orthogonal and I won't be able to excite the system. What's the problem? That defining something similar to the spin for these H states has been incredibly difficult to us. We found some correlations, and actually you're in that paper, I think. But that's, so let's say we found something that was something talking about chirality that was remain constant about the H state, but it was not as easy as we expected it to be. And since it was not that easy, the conclusions that we can extract from it are still, let's say, so, and we will see what we can extract. We will keep working. Well, we are still working on that.
I was wondering not only on the edges, but maybe in the bulk.
Absolutely, it's the same thing.
Also...
It's the same thing. I mean, and ideally, what you could do, but very ideally, is separate the band structure into two separate band structures, one for one chirality and one for the other, which is something that I think you can do in solid state physics. I'm not So you have Kramer's degeneracy, but if you break it, you cannot separate. I don't know. I don't know enough about solid state to. I'm learning on the go, but but I know that you can talk about states that have a well-defined spin and some other states.
Like a ferromagnet or something like this. Yeah, I see.
So, okay.
Thank you very much for the talk. I have a particular question. I think that it's a slide about Maria's work. Yeah. So it's just a very precise. Which are the ones that are on the figure below? The ones that perform the atomic phase.
Okay. Yeah, I mean, maybe from your seat you don't see it well, but there is a band gap here.
Okay.
And so it's basically this band gap, the one that presents the observed atomic limit. So all the bands below or this group of bands above.
Okay.
But yeah, so that's the critical band gap. Yeah. And here for the fragile phase is this collection of two bands that you have here, the ones that present the fragile topology. Where are the people from the photonics community? You don't ask anything, or no, they don't. I will tell Alex that you didn't ask.
Okay, if there are no further questions, then Aitzol again. In 2 weeks, we have the next. No? After
September.
September.
In
Okay.
September.
So we take a break until September.
Happy summer.
Yeah.